Hello. Um, Welcome to the last test that we have to do in Chapter 14. This is the um, chi-square test, Homogeneity of Populations. We had to actually look that up to make sure that how we actually pronounce that one. So I'm just going to the right slide. Minimize that. Okay. So, nope, this one. Oh, where is it? Here it is. Chi-square test for homogeneity of populations. Okay, so again, all of these chi-square tests their titles give you insight as to what test it is. So homogeneity of populations means homogeneous across populations. So basically, you're saying to yourself, from one population to the next, are they the same? Um, in goodness of fit, you're looking at one population and you're seeing if the proportions are equal. Um, in the test of association, you're looking at categorical variables that are usually presented in a two-way table, and you're seeing if the two categorical variables are associated with each other or are dependent upon each other. Um, and this one, you're basically, the null here is going to be that the null hypothesis is that the distribution of the response variable is the same in all populations. The alternative says that these distributions are not the same. So again, is the distribution the same across both populations? The alternative would just easily say that they're not. So, excuse me, the null and the alternative on all the chi-square testing are pretty much the same. Status quo for the null, and then the alternative is that they're different. So we have, again, a skewed distribution depends on degrees of freedom. For the degrees of freedom here, degrees of freedom, like the test of association, is row minus 1 times column minus 1. For the degrees of freedom in the goodness of fit test, it's categories minus 1. Okay, so um, let's, oh, and I want to say with this test, there are not many frappies on this. So if you're going to get a chi-square test, it's either going to be goodness of fit test or um, the test of association. This one, as you can see in the packet, there's only 3 of them. One is a frappy. The other 2 are textbook problems. And I said during class that the middle one in the 14.2 packet, you don't have to do, that's optional, but the last one you need to do. So um, here is the frappy that I'm going to be going over. It says in September 1990, each student in a random sample of 200 biology majors at a large university was asked how many classes he or she was enrolled in. The sample results are shown below. So here you have the table of the number of classes and then the number of students. To determine whether the distribution has changed over the past years, a very similar survey was conducted in September 2000 by selecting a random sample of 200 biology majors, and results from the 200 sample are shown below. And then you have the number of classes and number of students again. So this one is 1990, and those are your sample statistics, and this is 2000, and that's your sample statistics. So part A says, do the data provide provide evidence that the mean number of lab classes taken by biology majors in September 2000 was different from the mean number of lab classes taken in 1990? Now, hopefully you're saying to yourself, well, this isn't a chi-square test, and you are exactly right. This is going to be a not proportion, it's mean. So 2 sample t-test. Now, I'm not going to go through the writing up the parameters, the conditions, the calculations. I'm just going to show us on the calculator um, what the outcome would be based on this. So this was actually a number 6. So this is worth the most credit. Well, it's weighted the most on the AP test. It's the last one. And again, with the number 6, you're supposed to spend the most time on this one, as it is weighted the most. So I'm going to, my calculator is just coming up right now. So you're going to want to go to stats. There's my calculator. Okay. Clear this out. Stats, test, 2 sample t-test. Where is that? Where is that? Did I miss it? Oh, there it is. 2 sample t-test. Okay. So, we could input the data, but let's not, because then you have a frequency list and no, actually, wait, yeah. Yeah, to enter the data it wouldn't be beneficial. It just wastes time. They give us the statistics, so let's do that. So we have the mean number of lab classes in 1990. So let's put now statistics. So mean is 1.83, and the standard deviation is 1.29. And how many total? 200. X2, 1.93. And the standard deviation 1.37 and 200. And this would be a two-sided test because you're seeing if they were different. And again, with the t-test, we never pool. Although a p-hat combined with the two-prop z-int, that is a pool test. But they don't actually prompt that. They just do it automatically. All right, so let's calculate. And what do we have here? We have our test statistic coming out to negative 0.75, a very large p-value. Again, when we do a 2-sample t-test, it used that funky formula because a 2-sample t isn't exactly a t. So over the years, through technology, they have modified the degrees of freedom. And so here, with a really large p-value like that, and even if we did pick an alpha level, we would fail to reject the null. And basically, that with the 2-sample t-test, it's not showing that the mean number of lab classes from the two populations has really changed. Okay, now part B says, and I wrote that up right here. B says that the test in A, does the test in A address the question of whether, hold on, does the test in A address the question of whether the distribution of number of lab classes was different in 2000 than it was in 1990? If so, explain your reason. If not, carry out an appropriate statistical test using alpha equals 0.10 to answer this question. So here, what we would have to do is actually carry out the homogeneity of populations. It's saying if the mean number of lab classes were different, but it's not actually addressing whether the distribution has changed. So what we would do here is actually do the homogeneity of population. So it's 2 different populations. So the null again is the distribution of lab classes is the same in 2000 as it was in 1990. And the alternative is that the distribution of lab classes is not the same in 2000 as it is in 1990. And they told us to use an alpha level of 0.1. So here's my parameter in the chi-square test. And the next step in a chi-square test is to calculate the observed and the expected. Now, usually in both the goodness of fit test and the test of association, the observed is more obvious. This was a number 6 on the free response, so you actually had to come up with the distribution, you had to come up with the observed cell counts. So what I have here is I have the 2 populations, and you're seeing if in these two populations has the distribution changed. So you actually have 0 through 5, and all I did was I went over here and 0 in 1990, I picked up this number, and then in 0 in 2000, I picked up this number. And I did that the same thing from 0 through 5, and I put it in a table. So this is your observed counts. Now, the expected cell counts, we went over this in much more detail in the association, but basically what's happening here is you're trying to get the proportion of people that are in 1990 out of the total. So that's 200 over 400, and in 2000 it's 200 over 400. So basically it's an even split, which is why the expected counts are going to be the same exact number. Okay, so you have it's half. This says 200 over 400 times 48. So this really is row total times column total, sorry, over grand total. And I don't like to think of it that way, although that's the formula. I just like to think to myself, okay, well, what's the proportion of 1990 out of the total? Well, it's half. So it's half of 48, and then you do half of 134. If these two numbers are not the same, then the expected cell counts would be different, as we saw in the other test. All right, so basically, we look here, and all expected counts are greater than 5. Well, the exact words are all expected counts are greater than 1 and no more than 20% or less than 5. But the quick way that satisfies both is all expected counts are greater than 5. So calculations by name or formula, you would have to identify this as the chi-square homogeneity. I have a really hard time with that word. Homogeneity of populations or formula. So the chi-square, the formula would just be the chi-square test statistic. So you're going to take your 28, subtract it from 24, and square it, divided by 24. And then you're going to do the first one and the last one. So the last one would be 20 minus 10. Subtract those, square it, and divide it by 10. And now what you do here is you have to enter this in as a matrix, like I showed you in the test of association. And the interpretation is that, so here we get degrees of freedom is 5. We get a p-value of 0.068, and our test statistic is 13.821. So here we have a pretty low p-value, and it's much lower than what we have for our alpha level. So our interpretation is that since our p-value is less than our alpha, our findings are statistically significant. We will reject the null. There's evidence to suggest that the distribution of the number of classes is different in 2000 than from 1990. And time was running a little short, so I have a little bit more time to try to enter this in the calculator to show you. So test, and now we go to chi-square test, and you're going to enter this in. Oops, shoot, we got to enter in the matrix first. My bad. So matrix, edit. This is a, what would this be? Row by column. So how many rows? 2 rows by 1, 2, 3, 4, 6 columns. And we enter this in, and we get 28, 62, 58, 28, 16, 8, 20, 72, 60, 10, 26, and 12. Okay, so then we go stat, tests, chi-square test, not goodness of fit test, observed, expected. Now again, the expected is already calculated when you run it, so you don't have to enter that in, and then you just hit calculate. And you see there's your chi-square test statistic and your p-value, and then your degrees of freedom. So this is not a very common test, and again, you only have to do one more question on here, the last one, not the middle one. And that wraps up chi-square. All right, guys, see you later. Bye-bye.